postdoc at Florence Berkeley National Labs. She did her PhD at MIT. She's done a lot of interesting work on parallel dynamic and cache efficient algorithms, and today she'll be telling us about some of this recent work.
Thank you. Can everyone hear me? So yes, thanks, Julian. Today I'll be presenting my research in dynamic graph data structures as an example of this higher level algorithm engineering framework that I've been working on that I'm calling the Locality-First strategy. So like I said, the main focus of today is on this question called dynamic graph data structures. And the main focus of these data structures is to support both dynamic graphs and efficient query answering for multicores. I think everyone in this room here probably knows what a graph is, but they represent data with vertices and edges, and they underlie many fundamental applications. And because they're everywhere, there's been a lot of work on efficiently engineering these data structures, especially on multicores, but for other platforms as well. These days, large graphs like Twitter can fit into the primary memory on a single multicore, so we're interested in efficiently processing them in shared memory. And the focus of this work is on optimizing them for multicores. The goal of these data structures is to support the graphs in an efficient way to support queries or algorithms that one might want to run on the graph. So in this setting, queries are kind of complex, that, for example, like breadth-first search or PageRank or between centrality, like these classical algorithms, but you might be interested in running many others. And the goal is to make these data structures run as fast as possible to support queries while also supporting efficient dynamicity. These days, multicores are the most prevalent hardware because they're relatively cheap and accessible. For example, you can rent a pretty big one on demand from Amazon using just your credit card. When optimizing algorithms and data structures on multicores, there are two main important features. The first is multiple cores for parallelism, and the second is the cache hierarchy, which requires developing cache-efficient codes. So this is just an example of a multicore chip from Intel. You can see that most of the area is taken up by the multiple cores here, and there's a shared L3 cache, and all the cores have private L1 and L2 as well. So they have this pretty steep cache hierarchy, and this is great. Like you have multiple cores, you can take advantage of parallelism, but unfortunately, these two features also make developing code for multicores notoriously hard. There's been a lot of theses on trying to develop fast codes for these platforms and making really good progress and making it more tractable. So to be a little more specific, to take advantage of these hardware features, algorithms have to be optimized for both parallelism and for locality. Taking advantage of the multiple cores requires developing your algorithm to scale well in parallel, which is notoriously hard. And basically, you want to do your operations simultaneously and as many of them simultaneously as possible. The second one is locality, which is this property of algorithms. It's the tendency of algorithms or programs to access the same or similar memory locations over time. And people have developed these cache hierarchies to take advantage of this natural property in algorithms. But one thing that you might often want to do is trying to engineer your code to become more cache efficient, which is hard because you need to know something about the memory subsystem often, unless cache oblivious, which is a separate issue. But those are also hard. Yeah, so going back to graphs for a little bit, that's kind of high level why it's hard to do multicore engineering. There's several challenges, especially to doing these multicore data structures for graphs. The first is that graphs are naturally sparse, which is this property where most of the edges are not present. For example, in social networks, if the vertices are users and edges are connections, most of the users are not connected to most of the other users. For example, in a LiveJournal graph, which is this popular graph for experimentation, there's about 5 million vertices, but the average degree is 18, so almost all of the edges are not present. And sparse graphs appear in other domains, such as computational biology and road networks, and they all have different shapes, but they exhibit this edge sparsity. And sparsity is hard for locality, which is this property that we want to optimize for because of the presence of many zeros in your data, which affects how you would want to represent it. For example, the most straightforward representation of a graph is in an adjacency matrix, which we might often be interested in for ease of programming. But if your data is few and far between, then adjacency matrix is not great for your locality of data. Another part of the story is that graphs are dynamic, which means that they change over time. For example, if you have a social network, you might want to add or delete connections. And systems for these graphs have to support updates, edge insertions and deletions, as well as queries, which are these algorithms that you want to run on the graph. And supporting these dynamic graphs is challenging because there's sort of this inherent tension between locality and updatability that I'll get into a little more later, but kind of at a high level, the intuition is that if you put your data close together, if you want to modify it, it's more annoying because you have to move more stuff around. Despite these challenges to optimizing locality in dynamic graph data structures, there's been significant effort devoted to frameworks for these graphs by a lot of folks in this room. One recent shining example is Aspen, which is a really cool piece of algorithm engineering. It's really fast, it's beautiful actually, and it beats existing dynamic graph frameworks by several orders of magnitude, both in terms of updatability and inquiry time. And this is just an example on how fast Aspen, which is something that I did not make, can run these queries on Twitter. So it can do breadth first search in 0.3 seconds, it can do PageRank in 24 seconds, and it can do betweenness centrality in 4.7 seconds. And this is already really fast, like this is several seconds. But of course, we're always interested in engineering things to make them faster, because for algorithms, like the graphs are getting bigger, and you might often want to chain several of these algorithms together in some sort of analysis pipeline. So my co-authors and I introduced a system called Terrace, which is a novel dynamic graph data structure built around this, this framework that I'm talking about called the Locality-First design. And first I want to show some results about what happens when you use this method. This is a plot. The y-axis is normalized speedup of Terrace over Aspen, which is already fast. The line at 1 is equivalent, and the x-axis is just the several algorithms that we tried. So breadth first search, PageRank, betweenness centrality, and connected components. Up is good. Above 1 means that Terrace was faster than Aspen. And you can see that in these cases, these are averaged over several data sets, but in these cases, Terrace often exhibits speed up over Aspen. And both systems run the same algorithm because they implement the same high-level algorithm framework. And surprisingly, in some cases, Terrace actually achieves speed up over Ligra, which is a static system. And that is surprising because often you have to pay something for your dynamicity in your algorithm performance. But in some algorithm cases, you actually don't if you do this locality optimization.
Do you have to re-engineer the algorithm to use your framework, or is it like you can plug in?
Yeah, it's a really good question. So the question was, do you have to re-engineer the algorithms to plug into the framework, or I guess like the data structure?
Yeah. Or did you do that in this case?
So we separately implemented the Ligra abstraction. It's called like edge map vertex map abstraction. And one really nice thing about it is that it lets you write simple primitives that you can hook into your data structure. And as long as you implement the simple primitives, you can hook in any data structure. Right. One thing that I'm currently working on is trying to make that even more widespread. So it's a really good question. And one challenge in this area is like doing fair comparisons between data structures, because like the algorithms and data structures are somewhat orthogonal, and like you can imagine doing direct implementation of these algorithms and like writing your data structure underneath, but then it's hard to compare them. So, yeah. Thank you. So that was query performance.
Sorry, question along this line. So how much is the difference in code between, let's say, betweenness centrality and connected components?
In terms of, in the algorithm abstraction framework, not much.
No,
like the algorithm.
What you implemented, like in Terrace, when you implemented it.
In Terrace, you only have to implement the primitives. We use the Ligra abstraction, and the Ligra abstraction determines the algorithm, like it's sort of like a frontier type thing. So that the algorithms are pretty short, like usually they're about 100 lines or less. And if you implement the primitives through some layers of abstraction, you can implement some simple things like map, basically, down below in your data structure level. So that was algorithm performance. And the second in comparison when doing these dynamic graph data structures is updatability. So one thing that you don't really want to do, or like one thing that is not ideal, is to do really well in your algorithms, but then pay for it in terms of your updates, because then you're just somewhere else on this trade-off curve. So it is important to also measure the insertion throughput and also deletion, but it's not here. So here the y-axis is insertion throughput, up is good. The x-axis is batch size. And often in these data structures, we add edges in batches, which is like you have 100 or 1,000 edges that you might want to add at once. There's different ways that you can implement these batches. Terrace happens to implement them concurrently, but you can do something which is that Lakshman will talk about more in detail later, which is called batch dynamic, which is you implement them all as one atomic operation on your data structure. And the main point that I want to make here is that the Terrace line is this green one, the Aspen line is this brown one, and the green one is mostly higher than the brown one, except for the very last point, because Aspen does scale better for large batches. And that is something that we are working on in Terrace. But for almost all the batches, Terrace is pretty good relative to Aspen. So now that we saw the results, I want to explain how we got there. This work in graph data structures shows that to create these efficient multi-core solutions, we as algorithm developers and engineers might consider using something that I'm calling this locality-first strategy. This is like a temporal order for us to use when doing algorithm engineering. So the first step is to identify a problem that you might be interested in engineering. This problem that we just talked about is dynamic graph data structures. The next step is to understand the locality in these dynamic graph data structures, and then try to exploit it once you understand what is possible in the problem, and then only at the end to add back in the parallelism. So in the end, we want both locality and parallelism optimized codes because you can't achieve peak performance without both, but this is just a temporal order to follow because you have to pick something to do first. As I mentioned before, locality is this core property of algorithm access patterns. There are two main kinds that have been studied for decades. The first one is spatial locality, which is how many accesses an algorithm makes to nearby data over a short time. So ideally, you want to access contiguous memory locations, like for example, reading an array in memory is much faster than reading pointers, like in a linked list or something. And the second one is temporal locality, which is how many repeated accesses you make to the same data over time. And spatial locality takes advantage of things like cache lines, whereas temporal locality takes advantage of things like your cache levels, like L1, L2, and such. And so that's what I mean by hierarchical access. And temporal locality is something that you often change. Well, both of them are something that you often change your code to optimize for. But when you want to understand the locality in your problem, it's important to first understand like what are the options. So going back to graph processing, it turns out that if you want to optimize for queries in graphs, whether dynamic or not, it turns out that spatial locality is a main concern when doing that. And one really cool thing from the Liger work is this abstraction of several graph algorithms that allows us to express them in terms of something called vertex scan, which is this processing of a vertices incident neighbors. So this is two examples of graph algorithms. The first one is breadth-first search that you might learn in any undergrad algorithms course. The way it works is that you get a graph, you have your source, and you have a queue, and you put your source in the queue, and while you still have stuff in your queue, you look at the front, you look at all the neighbors of the stuff that you just dequeued, and then you explore them if they haven't yet been explored. And the main work in that was iterating through all these neighbors, because everything else is just kind of simple management. And that is what I mean by scan. So the second example is triangle counting, which is counting edge triangles in your graph. And the most simple algorithm to do that is you just look at all the edges in your graph, and you have U and V, and if they have a shared neighbor W, then you add to your triangle count. And doing this intersection, one simple way to do it is if your neighbor lists are sorted, you just do like this 2-finger scan, and you just count the shared neighbors. So that again is this vertex scan. And in the first example, you don't have temporal locality because you only iterate through every neighbor list at most once. And in the second one, you might have temporal locality. But the point is that you don't know if you're going to iterate through them more than once. So you have to optimize in your data structure level for spatial locality because the algorithm is sort of like at a higher level and you're not totally sure exactly what access pattern it has. And the spatial locality of the scan operation depends on your graph representation. So optimizing for scans boils down to choosing the right data structure. So for concreteness, this is an example graph with my co-authors. It's a pretty simple graph, but let's say that we want to represent this vertex here, and we're trying to represent the outgoing edges. So two simple representations that we can choose for this neighbor list is uncompressed, which is basically one row of an adjacency matrix, and edge array, which is basically one segment of your compressed sparse rows. And in uncompressed, you have a number of, in the unweighted case, you have a number of bits equal to the possible, to the total number of vertices in the graph, and then you set 0 if there's no connection, and you set 1 if there is a connection. In an edge array, instead of doing this implicit storage, you actually just directly write down the neighbors. So here, we wrote, like these two are the connections, so we write 2 and 3. And these are like pretty simple representations, but this shows what I was talking about earlier more concretely, which is that if your data is sparse, this representation is hard for your locality because you have many zeros, and so your data is far apart, and your scan is proportional to the number of vertices, no matter how much actual stuff you have in there. However, in this edge array representation, you get better efficiency on queries if you actually write down the neighbors if you have sufficient sparsity. So here, the scan is proportional to the degree of the vertex, which is great if the degree is much less than the number of vertices. So if you only cared about algorithm performance, you would be pretty much done here. This is basically this classical compressed sparse rows representation, and you would be great. But however, you want to do updates also. And so for example, like we were here, and let's say we want to add an edge to 0, and going back to these representations, we set the bit at 0 in uncompressed, so your update is order 1, because you just have to flip the bit. In edge array, however, it's harder, because if you want to keep these in sorted order, like for triangle counting in the earlier example, you have to shift everything down, which is now proportional to the degree, which is not great for arbitrary degree. So even these two simple data structures exhibit this tension between scan and update performance. And kind of the main question of these data structures boils down to how to do fancier data structures to support both fast scan and update. Like I said, state-of-the-art systems might use more advanced data structures, but they still have this tension from the previous slides. Folk wisdom about dynamic graph data structures says that you have a trade-off between query and update performance. This is just a cartoon, but like query performance, update performance, up is good, right is good. And in the extreme, for static systems, for example, Ligra, the query performance is really good, but like they don't support updates. So, and on the other extreme, you have highly dynamic systems such as Aspen, and the update performance is really good, but compared to Ligra, the query performance is not as good. I mean, this is like, it looks far in the cartoon, but in reality, it's not actually like that far. It's just for illustration. And like I was saying, Terrace achieves good query and update performance. The query performance is comparable to Ligra's, and the update performance is comparable to Aspen by designing these cache-efficient data structures. So like I promised, we're going to understand what is the opportunity for optimizing locality. So we understood that we're going to optimize for spatial locality. So the way that most of these dynamic graph data structures are currently designed is in this two-level structure. And this design is really good for parallelization because you have one level for your vertex IDs. Basically, each of these has a pointer to a separate container for the neighbor list. It's really good because you get to do parallelization over the vertex IDs. And you might not even necessarily care so much about the parallelism in the lower level, which is kind of harder to implement. This is the high-level structure that underlies a lot of these fancier data structures like trees, adjacency list, and others. Like you can make these boxes pretty much anything you want. They don't have to be even the same thing. So you get really good parallelization, but one problem in terms of optimizing for spatial locality in this design is that if you wanted to do, in some algorithms, you do want to do like an edge scan over the entire thing, like in in the most simple version of PageRank, you do like a scan over the entire thing, and you have to incur cache miss at the edge of each of these neighbor lists, which is not ideal for your locality. So that's one possible way that we can improve it. So going back to this high-level strategy, we started with the problem, we understood the locality potential in it, and now we're going to exploit it using fancier data structures. So like I said, this high-level design that underlies a lot of these data structures is you have two levels. One is a pointer to all these containers, and you have a bunch of separate containers. And the first step that my co-author and I took to trying to improve the locality is to collocate all of these neighbor lists into one giant data structure. And so this solves the cache misses that you get in between the vertices when reading all of the edges. But it does introduce some issues because if you want to do concurrent updates to multiple different neighbor lists, now you have to deal with the concurrent data structure on the bottom level, whereas here you could just do them separately in parallel. So it does introduce some issues. So you do have this, again, this tension between locality and updatability. But it turns out that because this is contiguous and computers are really good at doing stuff in contiguous memory, the updates in here are still OK. And that was our first paper on PPCSR. And one question that this design raises, I guess both during and after we were working on this, is that like whether these misses that I'm talking about at the end of the neighbor list actually affect your performance, or whether they're just kind of like a low order term, because you do have to, in some algorithms, like access the entire graph. And so you might, depending on the structure, like if you thought, or like one kind of thought experiment is like if all your neighbor lists, oh, I'm sorry, go ahead. Oh, okay. I could finish the slide and then.
Okay. You have CSR there, but then at the bottom you have packed memory array, and I'm just wondering, like, where is it? Like, I see CSR, and I think, how is that different than CSR? But it is a packed memory array that you're using?
Yes, it's a good question. So this thing, if this was an array, this would be CSR.
Right.
And if this is a packed memory array, this is PPCSR.
Okay. So PPCSR is a packed memory array.
Yes, it's
Okay, got it.
with like a top level. Sorry, and I guess for folks on the stream, the question was, what is the difference between this picture on the right and CSR? Yeah. So basically what I was saying is that one thought experiment that we can do is if all the neighbor lists are of huge size, like if they were 1 million or 10 million, for example, you wouldn't really care so much about the edge condition at the end because you're already reading so much data, like saving one cache miss is not going to help you that much. But if they were tiny, like in the extreme, like if they're 1, then you would actually care. So a lot of this depends on the structure of your graph. And it turns out that yes, it does actually help you because of this natural structure of real-world graphs. They naturally exhibit this skewed structure, or like power law degree distribution, where you have a lot of low-degree vertices and a few high-degree vertices. So this is a cartoon of, I guess, Twitter. The y-axis is the frequency of occurrence. The x-axis is the number of followers you might have. I'm here somewhere, and Taylor Swift is here somewhere. I don't like most people are kind of like me, where we don't have many followers, but you have these few heavy vertices. And if you run some statistics, you can see like on Twitter, over half of the vertices have fewer than 10 neighbors, and almost all of them have fewer than 1,000 neighbors. So most of the cases that most of the neighbors or most of the vertices have pretty low degree, so you do actually care about this edge condition. But the variance is very high, like the max is in the millions. So the next step, we started with PPCSR, which is collocating everything into one giant data structure, and that's this picture on the left. The problem with this initial design is that the high degree vertices slow down updates for everyone. So like if you want to add vertices into, or if you want to add degree to a heavy vertex, the time everybody else has to deal with the heavy vertex in your data structure. And so this refined solution is using this hierarchical design that co-locates low degree vertices for improved spatial locality in cases where it actually matters relative to the degree, and separating out higher degree vertices where you already have to read so much data that it doesn't really matter that you save 1 or 2 cache misses, and then trying to optimize the updatability in those. And Terrace implements this hierarchical skew-aware design using a shared PMA and a standalone B tree. A PMA is a dynamic array-based data structure, and a B tree is a dynamic tree-based data structure. And B trees are asymptotically optimal, while PMAs are not. But it turns out that if you use this, but in practice, like the theoretical bounds, as I will show you in a second, are not exactly what they seem. And the reason for this multi-level design is this practical trade-off between PMAs and B trees. So the theory tells us that B trees are always better or match PMAs in terms of the asymptotics in the classical caching models. So if you only cared about the theory, you would pick B trees and be done with it. However, the reality is more complicated because in practice, neither is better for the operations that we care about in all aspects. So this y-axis is doing just like a couple of micro benchmarks with PMA and B tree. Y-axis is PMA over B tree runtime. So this dotted line is at 1, and above 1 means that the PMA was slower, and below 1 means that the PMA was faster compared to the B tree. The y-axis or x-axis is just the number of elements in the data structure. And these 3 lines are these classical data structure operations: get, insert, and scan. And you can see that the B tree is better for get and insert because this line is above 1, and the PMA is better for scan because that line is below 1. And the reason for this is that the classical caching model doesn't take into account the difference between sequential and random cache access. So in the regular external memory model, any arbitrary memory block access has a unit cost. But it turns out that in reality, accessing adjacent memory blocks is faster than accessing random memory blocks. And there are more advanced caching models that take this into account, like the affine model, for example, has some parameter that takes that into account, but those are not yet as widespread as the traditional caching models. So that's one interesting direction, I guess, which is to think about how we might use the fancier models and whether that captures what we see in reality, or whether those models also need refinement. But yeah, but anyway, going back to graphs, the problem with this is that neither data structure is a clear winner for the operations that we care about, and the solution in Terrace is to use both depending on the degree. So now we have this background to understand how Terrace takes advantage of spatial locality. As a further optimization for locality, Terrace stores some of the edges in place as an additional optimization. Like if the degree is very low, then you can just store them in place in some type of array. You don't even need to go to a separate neighbor list, but that's kind of like it doesn't fit as well into the story that I was trying to tell. And this is just a measurement of cache misses on the live journal graph to understand this thing that I was talking about in locality. We have 3 systems. We have Ligra, Aspen, and Terrace. Aspen and Terrace are dynamic. And we tested this on 2 algorithms, breadth first search and PageRank. And basically, the only point I want to make here is that these numbers are relatively smaller than the other ones because of these cache optimizations. Yes?
What is the space usage or difference in space usage?
That's a very good question. So the question was, what is the space usage? Terrace is bigger than Aspen for several reasons. One is the PMA uses a constant factor of extra spaces, while B trees use asymptotically less than a constant factor of extra space. Also, the implementation of Aspen is compressed. They use delta compression, whereas the current implementation of Terrace is not compressed. But that is something that we're working on, and I think it would be a really interesting direction. So the results that I was showing at the very beginning show that Terrace is about twice as fast on algorithms compared to Aspen with similar updatability. And the cool thing about these results is that the main driver is this locality-first method for optimizing for engineering practical algorithms that enhance your spatial locality in this case, but in general, all kinds of locality in other cases. And in the end, notice that I didn't really talk about the parallelism at all, but all of these systems do happen to be parallel because they wouldn't be really competitive with each other otherwise. And the code is at this GitHub. And I want to maybe switch gears a little bit. So we just finished, there's kind of 2 parts to this talk. There's a surprise second part. The first one is this dynamic graph data structures using this locality-first strategy. So we kind of walk through a case study. And I want to talk a little bit about stuff that I'm more recently working on in this area. But first, I can stop for questions. So I mentioned briefly about this batch parallel model for data structures, where you have, so there's kind of 2 ways that you can do updates on your data structure. The first one is concurrent, which is like a classical model for key value stores and other kinds of data structures. The second one is batch parallel, which is you have a set of updates that you want to make, and you make them into one atomic operation on your data structure, and you can algorithmically support those, often by union. And yeah, so because often batch parallel implementations are faster than the concurrent counterparts, there's been a lot of work in developing efficient batch parallel set implementations, which are the underlying thing for, you can build any graph data structure out of an efficient set because you just make the set like one of the boxes that I was showing in the high-level design. So there's been a lot of work on doing these fast batch parallel sets and maps. And the main bottleneck in the parallel scalability is not necessarily, if your batch size is big enough, it's not necessarily the parallelism. It's kind of like the memory subsystem limitations. Because just that's it kind of always happens in multicores if your data set is big enough that you run into these memory scalability issues. And yeah, and so people have done a lot of cool stuff to try to get around this, mostly compressing the data structure, but also doing other tricks. And one thing that I'm interested in working on and have been doing is to use this cache friendliness of packed memory arrays with algorithmic support for batch insertions and deletions. So the thing in Terrace was concurrent, but it could be way faster if you had direct algorithmic support for batch updates. And the problem with developing these algorithms for PMAs is that existing algorithms are mostly for pointer-based things like skip list or tree. So existing algorithms don't port super easily to the array model because they often rely on pointer union, like tree union and pointer adjustment. And this picture is tree union.
I think I'm confused. What was the difference between batch parallel and the concurrent?
Yeah. So the question is, what is the difference between batch parallel and concurrent? In concurrent, all the updates happen in parallel to each other, but every update is an atomic operation, every single insertion. Whereas in batch parallel, the group update is one atomic operation. You say for example, for a batch size of 100, you would say, I have 100 updates and I want to do those in one single atomic operation on my data structure. So you can do something like tree union basically, whereas you cannot do tree union for the concurrent world because like the entire union or like each update is not concurrent to each other.
Sorry, why does tree union help? I guess I don't have enough.
I see.
Yeah.
The reason is that for efficient parallelization, often you need enough enough work to parallelize over. Like parallelizing each of these insertions is like log time. So like parallelizing within the insertion is often not really helpful. So if you get to be in the batch world, you get to parallelize over the entire batch, and you get to like modify. You kind of like have some guarantees where you can modify parts of your data structure with nobody interfering with you.
Right.
So you don't have to do like concurrency control, for example.
Right. Okay.
So I have been working on this a little bit. So one thing, this is currently on archive, we made CPMA, which is a compressed packed memory array with batch insertions. And this is, I think it's a little cool because like a lot of the batch parallel sets are pointer based. I think almost all of them are. So it's not, so like up front, it wasn't actually clear that this would be better. But so here's some data. The left side is batch insertions. The y-axis is throughput. The x-axis is batch size. There's 4 lines. One is PMA, one is CPMA. Both PMA and CPMA have batch insertions. There's UPack and CPack, which is very recent. It's in a library called CPM, but I don't call it CPM because that's just like edit distance 1 for CPMA. So I'm calling it UPack, which is uncompressed back trees, and CPack, which is compressed back trees. And there's 4 lines, and the main point that I want to make here is that the compression improves the yellow one is compressed and the blue one is uncompressed for the packed memory array, and the yellow one is higher than the blue one, and both are higher than the other ones, except for the last one again. And this one is range queries. So the only reason that we actually would ever want to use PMAs is because if you have some kind of scan-based workload, because a PMA is basically an array, so you want to scan over a large part of it. Otherwise, like if you're doing update only, often you would just use trees. So here for range queries, y-axis is throughput, x-axis is like size of your range query. Again, these two kind of like x star lines are CPMA and PMA, and these are tree. And in the limit, they kind of converge a little bit because it actually turns out I think the default node size in CPack is pretty big. So yeah, so that's why they're pretty close in the limit. But the CPMA does have the advantage of being an array, so it is fast to scan. So this is kind of interesting, I think, because there's often a trade-off between insertion and scan. But it turns out that using batch insertions, you can, in the PMA and CPMA, you can overcome a lot of this trade-off. And I'll tell a little bit about how you do it. So PMA insertions, a PMA is an array-based data structure. And there's several steps to doing a PMA insertion. So like, let's say you have this array, and the way that a PMA works is it's basically an array with spaces inside it. So you don't have to shift everything around on every insertion. And so I want to insert this number 22. So first I look for where I would put 22, which is here. I do like a binary search. And then you place 22. So here you would put 22 in its order in sorted, or like in its location in sorted order. And then one of the main properties of this is that you have to maintain some notion of density in all of these segments. And so after you do an insertion, you have to count your segment. And if you violate your density bound, you have to count your neighbor segments and do some redistribution. So here in this example, the density bound is 0.9. And I count this segment, and I find that the density is 1, which is higher than 0.9. So I count my neighbor, and I find that the density is 0.5. And you can equalize them to both satisfy the density bound. So that's what redistribution is. You put some of the elements from the overfull segment into the less full segment. So now 15 moved here, and both of them are happy. So that's how point insertions work in PMA. And like, this is an example for 2 segments, but if your array is of arbitrary size, then you basically build a binary tree on these segments, and that's how you do the redistribution. So it is not clear how to do tree union in arrays, because there's no pointers in this insertion. And the high-level way that this multi-insert works is kind of how you might imagine it through batch merges. So instead of inserting 1 element, this batch insertion has now 3 elements that you want to add. So, for example, like 15, 22, 89. And let's say I have this PMA with some empty slots in it. And to do the batch insertion, I search for all, or like for the segments that these elements would go into. And I find that they all go into the segment, which is a little unfortunate because there's not enough slots for all of them. Like there's only 2 empty slots and there's 3 things that I want to add. So this is one subtlety, which is like you have to, if you're doing batch merge, you might not have enough space for it. And so one thing that we did is like in this batch merge phase, you might have to use some external storage or like some other out of place storage to store the full thing that you want to merge. And then this 5 is just the number of elements in your out of place storage. But counting still kind of works the same. Actually, counting now is easier because you just divide this over the number of slots that you have if you know that you have out of place storage. And again, like this 0.25 is less than 0.9, but this 1.25 is higher than 0.9. So you want to do this equalization. And so you move some elements from this out of place storage into the less full neighbor. The most hard part of this, which I'm not going to get into, is that doing this counting work efficiently is subtle. Traditionally in the concurrent world, you might have to, if you counted them concurrently at a high level, you might have to like different threads might recount the same area if you're not doing efficient caching. So one thing that the main algorithmic challenge is to do this work efficiently. But the actual batch merging is really fast because it's just moving arrays around.
Just a question. Do you make an assumption that the size of the batch is smaller than, like, I guess, the contiguous sub-segments that you're looking at?
The question was, do you have to assume that the size of the batch is smaller than the segments? No. In this case, if this was like larger than the segment, the out of place storage is as big as you want. And so you would just write how many elements are in the out of place storage. Like it could be that your batch is gigantic and they all go to the same place. But then you would just use this large out of place array, and then you would write the number of elements in there. And then you would redistribute over a bigger area potentially than the way that PMA insertions work is that like if you find that your neighbor doesn't have enough space to hold all your elements for them both to be happy, you like go up 1 level in the tree and you keep going until you find one that can make everyone happy, or you just have to double the entire array. Okay, so one reason that we were interested in doing this is that, like I said, the main issue in the scalability is often not the parallelism, but the memory bandwidth. And so the batch insertion algorithm that I just showed you is for PMAs, but you can easily translate into compressed PMAs. And so we did this is just classical parallel scalability. This line is CPMA, this line is PMA, and this is the number of threads. And the CPMA has higher parallel scalability than the PMA because you have to just move fewer bytes around. And you kind of see a similar thing for the range queries.
How much smaller is CPMA compared to PMA? Based on this, that plot seems that this difference is significant. I guess like the speed up cannot be more than the difference in size.
Yeah, it's a good question. So the question is like, how much smaller is CPMA compared to PMA? It depends on how many elements you have in it, but if they're closer together, then your compression ratio is better. We often saw compression ratio like almost around 3 or 4.
3 or 4, right?
For sufficiently large data set size. Yeah, so to bring it back to graphs, one cool thing about the CPMA that you can do is that you can think of your graph as just one giant sorted edge list, where you have like U and B as two parts of your edges. And if you put them in, if they're less than 32 bits, you can use 64 bits to store both the source and the destination, the source in the upper 32 and the destination in the lower 32. And you can also do this if you have more than 32 bits, but you just need two 64-bit things together. You can store this list in one single CPMA. And if you use compression, so like, for example, you have these edges like UV, UW, UX, and this is how you would store them in a PMA in 64-bit chunks. So like each of these is 32 bits. So you have like UV, UW, UX. And with delta compression, you often elide out the source. So you have U, which is your source, and then you have V, which is the or neighbor, I guess. But then you have like W minus V and X minus W. And then since you subtracted out each of these chunks, you got rid of U in almost all of the rest of them.
Can you store 0 in 0 bytes somehow?
Can you store 0 and 0 bytes? I think you have to use 1 byte to store 0. I think the minimum space per thing is 1 byte. Well, for byte codes, but like you can use smaller codes. Like, you can use like 4-bit or 2-bit and 1-bit. But I think they tried those in Ligra Plus and they weren't very fast. I think that's why we stuck to 8-bit. Yeah, and then we tried this for dynamic graphs. So in the CPAC paper, they also do it for dynamic graphs. And then we did several algorithms. So this left side is algorithms. Up is good. This is algorithm speed up. And fgraph is the one array thing that I just showed you. The F is for flat, I guess. And this one is update speed. Up is good. Y-axis is throughput. X-axis is batch size. And now that fgraph has actual algorithms for batch updates, the batch updates are comparable to CPAC. So let's wrap this up. Despite this theoretical prediction that PMAs are worse than B trees or cache-friendly trees, CPMA empirically can overcome this trade-off by doing locality-based optimizations. And this is just, again, like a similar cache miss table that I was showing earlier. This is L1 and L3. This is UPAC, which is uncompressed, CPAC, which is compressed, PMA and CPMA, this is uncompressed, this is compressed. I guess like the interesting comparisons are like this and like this. And so PMA has more cache misses than CPMA, and both of them have fewer cache misses than even the compressed tree, because it is contiguous and so it gets to do really fast scans. And yeah, you can find the details here. And yeah, thank you. So one thing that I'm really excited to talk to folks about here is this relationship. So I talked a lot about like dynamic graph containers, which is how you actually store the graph. But I want to know more about the relationship between the container and the dynamic graph algorithms, which are actually really data structures, but that's okay. So like obviously to do the algorithms, you have to store the graph in some kind of container and you have to choose a container. But like, is there also a container question in the dynamic graph data structures, which are called algorithms? Yeah, so I'd love to talk to folks about that. Thank you.
Any questions?
So you used some kind of portfolio type of approach.
Oh, sorry.
So you used some kind of portfolio type approach.
Oh, I think it's not.
You used some kind of a portfolio type of approach for choosing like which data structure you use based on the degree, I guess. Was this always like, you know, could you extract a clear rule of thumb, or is there some potential for using some, I don't know, more data science or machine learning type of thing that predicts like when you should use which data structure?
The question was, live stream here?
Either way.
Okay, yeah. So really quick, the question was like, could you kind of choose the cutoff in a smarter way, maybe, in Terrace? And I think it's really interesting. Currently the way we did it is just like some very simple heuristic based on the memory block size. I think like between the in-place level and the PMA level is just like a cache line or two, and then between the medium level and the big level is like a page size. We did like a little experimentation around those areas, like within maybe a few powers, and found that it didn't really affect things that much, just because like the variance is so high that like the really heavy vertices are so much heavier than everything else. But I do think that there could be definitely a smarter selection, and maybe even more data structures. Like I guess there's nothing like magical about 2 or 3, if you did have a reason to exploit different trade-offs.
I have one question. So you mentioned that your data structure is concurrent. Do you use like a lock to support concurrent updates, or do you have some other way to do it?
Yeah, so the question was like, how do you do the concurrency? The PMA uses locks within, because it's one single shared PMA, and the B trees are separate, so you can just lock the entire B tree. But one thing that I think you could do to make it faster is to make it a concurrent B tree, or even a batch B tree, but then you're in the batch world.
Thanks. Okay, well, let's.
All right. There's one more question.
Oh, there was one more question. Sorry.
Maybe a general question about like is the graph data structure you're using is it for a main memory data structure that you use for a specific application, or do you anticipate like that it could be the same graph could be used for maybe many different computations, maybe different from the applications you have seen here? So how much of your design is based on the specific algorithm or problem you want to solve, rather than I just have a generic graph data structure and maybe I may run many different algorithms on it?
I see. So the question is like how much of the design is based on the, in some sense, like the algorithm. Using the scan abstraction, you can express like a huge variety of algorithms. I think in like one of the follow-up papers, they do maybe even like 20 or 30 algorithms that you can use with scan abstraction and a little bit of other stuff. So I think that the variety, like the base idea for what you're optimizing for is pretty wide, depending on the kind of algorithm that you might want to run. One really interesting thing that if anybody has ideas, I'd love to talk about is like even more like downstream applications. So like right now we have this LIGRA framework and we can run algorithms, and maybe the algorithms can plug into some even bigger downstream application that uses those as components, or maybe does other stuff. And then it might be that in those other applications, you might care about other things besides scan. Another thing that I think Bill was talking about earlier is like this, maybe like we are currently optimizing for both update and scan, but one question that I'm not sure that anybody really knows yet is like we know like how fast the edge insertions come, but I don't think that corresponds necessarily to the underlying graph representations, because like I think like, for example, in a social network, you might add a friend, but I think probably companies keep a lot of other metadata that they're interested in maintaining in the graph. So yeah, so like, I guess like the question is like, should this update scan trade-off be a weighted function? And if so, what should the weights be? I mean, if you can do better in both, then like, I guess fine, but like, could you pay one for the other, and should you?
Great, thanks.